All right, let's go ahead and get started. My name is Vijay Gupta. I am in EC department. So first of all, I would like to welcome you to the Kaiqing seminar series. This semester, as always, Kaiqing has lined up with great speakers, and I hope that we'll continue to see such a robust participation through the semester. It's my great pleasure to welcome Dr. Kaiqing Zhang to the campus. Kaiqing got his bachelor's from Tsinghua and his MSc and PhD from UIUC. He did a postdoc at MIT, and now he is in University of Maryland. I never figured out whether one calls one's postdoc institution their alma mater or not. I did a postdoc, and so I have very fond memories of that place. Especially for the students and postdocs, what's sort of very inspirational about Dr. Zhang is not just the very high intellectual content that is in his papers, but how beautifully his papers are written and how prolific he is. Those three qualities are together are very, very hard to find, especially in somebody as young as Dr. Zhang. And it's no wonder that he has been recognized with many, many honors. He's probably beyond the rising star. He's a star in the field now. He has been recognized by different communities. So his NSF career is from controls community. He has an AFSI Award. He has also won best paper awards at ICML, young faculty award at AAAI. He has been given research awards from companies like Cisco, from foundations like Open Philanthropy. And what is particularly inspirational is his George Corcoran Leader in Education Award, which again is something very special because he takes education and presentation very seriously. So we're very eager to learn more about principled AI agents. So.
Thank you so much, Vijay, for the super nice introduction. It's really my great pleasure and my great honor to be here. Actually, it's my first time visiting Purdue, and it's really nice to see a lot of old friends and meet a lot of new friends. It's really my great honor to be here. Thank you so much, Vijay. Today, I'm gonna share with you some of the things we have been doing lately regarding how to develop principled AI agents with decentralized and asymmetric information. So before I forget, this is a joint work with a bunch of amazing collaborators. My student Xiangyu at Maryland, and Yang and Jiris from Yale, and my postdoc advisor Asu, and also a collaborator Chen Wu. We've been mainly talking about two papers I highlight here, which was accepted at Europe's 2024 and the ICLR 2025. If time permits, I will probably also talk about this SIAM paper on control, accepted to the SIAM Journal on Control and Optimization, but we'll see how far we can go. So maybe background. So over the years, we have seen significant progress in developing autonomous agents with applications like board game agent or large language model agent, with applications like coding, robotic manipulation, playing video games, as well as e-commerce. So specifically in this context, I'm going to talk about today, when we say AI agents, we mean AI models for decision-making tasks, especially for decision-making tasks in dynamic environments. In fact, if you take a closer look at many of these success stories here, they naturally involve multiple AI agents interacting with each other. And oftentimes with the interaction with humans, if you view humans also as an agent for decision-making. Okay? Like, for example, in playing Go games, there are two agents playing the game, and it's a zero-sum game in the sense that the win of one side is the lose of the other. Okay? It's dynamic because you have to make sequential moves in order to win the game. Similarly, in this human-machine interaction in self-driving car, robotic manipulation in playing video games, and the fleet control robots in warehouses. So multi-agent scenarios by nature. Therefore, it has inspired many new results on the theoretical foundations for understanding multi-AI agents recently. In particular, I've been asked the question quite often. If you try to understand this multi-agent decision-making and learning, what are really the unique challenges you need to address here? Okay. if you move from single agent to multi-agent, if you develop an autonomous car program in your simulator, but if what's really happening is something on the right-hand side, what will really happen? In my opinion, there are several unique challenges from my experience of studying this area. So the first one I think is very interesting and important here is the non-stationary and strategic nature of the environments. But that I mean that while you are learning as an agent, other intelligent agents and humans are also learning and adapting. And in fact, many of the AI agents nowadays, they're oftentimes built with a single agent mindset. If you take large language model as an example, so they were trained to predict next token, or if you use reinforcement learning to train it, usually it's modeled as a Markov decision process where you try to maximize a certain accumulated expected reward. They were not trained for such a multi-agent environment. So another challenge, usually people talk a lot in this multi-agent setting is about scalability. So as we know that the algorithm may grow like exponentially as the number of agents grows. So that's why people develop a lot of like decentralized learning algorithm. For example, they just plug in some single agent algorithm on the agent as if there doesn't exist any other agents in the environment. We call decentralized learning in general. However, this decentralized learning is usually very hard to analyze, and it's unclear whether they're applicable to many of the scenarios where they are by nature involve multiple agents. Finally, I think probably is the focus of this talk. I'll emphasize here is that I think another very important and unique challenge here is regarding information. Okay? So the agents usually share, they receive different information. They have asymmetric and decentralized information during learning. They have different view of the world. They have different experience with the world. And AI agents are trained oftentimes with some privileged information, meaning there is some asymmetric information, not only among different agents, but also among between training and testing, as we will see more later. Especially you work on robotics, you will see that, for example, these agents are oftentimes trained in simulators. Okay? And in simulators, oftentimes you have good access to some of the information you don't have if you deploy these policies. And we will see this kind of asymmetric information will also play a significant role in terms of the understanding the efficiency of these learning algorithms. So based on this kind of context, we are trying to understand AI agents with asymmetric and decentralized information. If you really try to move from single agent setting to the multi-agent setting. As I mentioned, when I mentioned AI agent in this talk, we are talking about the agent interacting with the environment, with the world, taking action, and then receive some observation or feedback from the environment. And they will keep iterating this process and make sequential decisions. In the first part of the talk, I'm going to talk about some understanding about reinforcement learning agents. In particular, how do they address this asymmetric and probably also decentralized information provably? And second part is kind of like our initial kind of exploration in this domain is regarding, can we better understand large language model agents, LLM agents? So in terms of understanding the question of how to better enhance their strategic and decentralized decision-making capabilities with some principles from control theory and reinforcement learning theory. So let's dive in. The first part is regarding RL agents with asymmetric information. So in particular, reinforcement learning has been predominantly studied under the model of Markov decision process, where the system states are perfectly accessible. However, in many practical applications, let's say robotic manipulation or self-driving car, or even playing video games, the agents only have partial or noisy observations almost always. And this is even more so in the multi-agent setting, like in this OpenAI's example playing hide and seek, each agent has only very partial and local view of our environment. And you may also see such examples in playing like card games like poker or mahjong. So agents have imperfect and decentralized information about the state, as well as other agents' information. So this is why it's even more complicated than the single agent setting. So in theory, it's very hard. Okay? Learning with or decision making, even decision making with a partial observability is very hard. So in the single agent case, in theory, we know that planning the optimal policy, meaning even if you know the model, I want to find the optimal policies problem, is piece-based hard. And also recently, people showing that it requires exponentially number of samples try to learn such optimal policy if you don't know the model. Okay, this is a single agent case. So which means that neither computationally nor statistically efficient algorithms exist in general. In the multi-agent case, the complication kind of get exaggerated in the sense that in the multi-agent case, computing the T-optimal policy, even with only 2 agents, could be double exponentially hard in the worst case. Okay? And also, even if you are not caring about the sequential decision making, if you are only looking for a single step optimal policy in decentralized decision making, we also know this is NP hard problem. And also in control theory, we know that there are also some very intriguing like counterexamples in decentralized stochastic control where they call Wilson-Hanson counterexample. Because of this asymmetric information, even if the system is linear, but there exists a nonlinear optimal policy that is strictly better than linear ones. So the reason why I list all this like pathological kind of results is that decision making and learning with partial observations are hard in general, and it's a well-known fact. Any questions? Also, by the way, I really want the talk to be interactive. If you have questions, just raise your hand, okay, so that we can discuss. Just interrupt me. But meanwhile, in the empirical world, if you really talk to robot learning people, okay, I would say this robot learning is one of the most successful examples of applying reinforcement learning, especially deep reinforcement learning in practice. So if you talk to them, they told me like actually partial observability is not that big problem. It's not being a huge barrier to them. Okay? There has been actually many success stories that build upon partial observable reinforcement learning. For example, in robotic manipulation, that was OpenAI's learning dexterity, okay, for manipulation. And this is another example from a group at ETH, Professor Marco Halter's group, working on reinforcement learning for locomotion. Okay? They really scale up deep RL in locomotion and also in OpenAI playing Dota games. These are all partial observable environments. If you really talk to them, how did they make this work? I think one key algorithmic ingredient here is to leverage privileged information. By saying that, what I mean is that privileged information here means some additional information you are available during learning, during training. And in fact, only during training. Specifically, it oftentimes refers to the following thing. In a single agent setting, it could be the state of the problem. Okay? Think about the partially observable Markov decision process. At simulate in the training phase, you have access to the simulator, so you have access to the state of the environment. You can leverage that state in your training to get a better policy. It could also be coming from like a high precision sensors during training if you don't have a high fidelity simulator. In the multi-agent setting, there are also some other privileged information people use in training. For example, it could be like people in multi-agent RL, people call it centralized training with decentralized execution. So basically means that at training time, you are able to leverage other agents' information. You can aggregate that information. Although you are not able to use that when you really deploy such a policy, because you use that in training. So in particular, I'll take this example. So at training time on the left-hand side, that's where I think from Lee, that was the locomotion paper using reinforcement learning I mentioned. So you build up a very high fidelity like simulator. You can simulate the terrain, you can simulate the movement of the machine of the robot. But what's really happening is on the right-hand side. You only take partial observation as input. Similarly, in the self-driving car example, you may have like a top-down camera. You may be able to track the state of all other agents. But you are not able to see that fully when you are deploying this policy at test time. And the last one is a very popular paper, empirical paper on multi-agent reinforcement learning, where they aggregate the information of other agents at training. And actually, that was a paper they invented the name of CTD, centralized training and decentralized institution. So basically, at training time, as you can see, you are able to aggregate other agents, observation, and action. You use that to train your Q function, as we'll make it more formal later. And then you learn a partial observable policy and deploy that in a decentralized environment. But to emphasize here, one thing to note here is that the final goal here is unchanged. You still want to learn a partial observable policy that can be deployed without this privileged information. So that's the ultimate goal here. Any questions so far? Great. If you are, especially if you are, I think for this community, if you are working on like robot learning, you must be very familiar with this pipeline. This thing I just introduced to you. So let's try to make it a little bit more formal. The problem we are trying to address here is modeled under partial observable MDPs, Markov decision process. So in particular, at each time step H, this agent will observe something, observation OH, from this emission function, big OH. It's conditioned on the current state. I don't have a perfect access to the current state SH. This is a fundamental difference from the fully observable reinforcement learning, where you have to see the state SH. And then the agent takes action H, receives the reward RH, and system transitions into the next state SH plus 1. And in general, for this agent to make optimal policies, you have to take into account the whole history so far. Okay? It's not sufficient for you to only look at the current observation to make decisions. That's not optimal. You have to look at the whole history, tau H, which is a summary of all the observation, the actions so far until time H. Your policy is conditioned on that, instead of conditioned only on the state. And the goal here is try to still optimize some accumulated expected reward. And the generalization of that is in this multi-agent setting, where at each time step H, agent I observe a different version of the observation with a different observation channel or emission function, conditioned on the global state, SH. And also they take their own action, AIH, receive some reward, RIH, which could be potentially different across different agents as well. So in other words, it's possible that they may have misaligned objective. And then the system transitions to the next state. In fact, this is a generalization of the fully observable Markov game model or stochastic model, game model originated from Shapley back in 50s. In fact, if you look at almost all the recent development of multi-agent reinforced learning theory was based on this fully observable Markov game model. There are several results, including one of my results here. We'll focus on the Markov game model, where you do have access to this. But this model is a strict generalization. It's fundamentally harder than that, and we will see later. And when the agents share the same reward, we call the cooperative setting. Okay? We also call it cooperative QSG in this context. In fact, in that case, if you are looking for the team optimal solution, it's also referred to as a decentralized partial observable Markov decision process, okay? Or DAC-DP. You will also call it. And this is an illustration of that setup. And now let's talk about the solution concept we are looking for here. So in this multi-agent setting, for each agent I, at each time step, they will act according to some policy, pi IH, condition on the history you have received so far, tau IH. This tau IH could be a subset of the joint history so far, because potentially we'll see later that the agent may share some information with each other. Okay? You may receive some observation and action from other agents. And then if you define this accumulated expected reward for that particular agent I as your objective, which is denoted as JI, you will realize that this objective is a function of not only your own policy, pi I, but also a function of opponent's policy or other agent's policy, pi minus I. We use minus I to denote all other agents' policies. Okay? Because they enter the picture through both the transition I introduced, as well as the reward. Because the reward here, although each agent has your own like RI, but the state and the observation, state and action, they're all joint. This action includes your own action and others' action. Let's call this expected value of agent I. Then in this multi-agent set is not, optimality may not be well defined. If you consider a case where the agent have different reward. Instead, a more common solution concept here is the equilibrium. Basically meaning that at this point, at this equilibrium point, which is a joint policy, pi I pi minus I, there's no incentive for any of the agent to deviate. If you fix other agents policy, like as this pi minus I, and if I choose this pi I, it's the best response I should do. It's the best option I should take. If this pi, they are kind of independently determined, we call this a Nash equilibrium. If you allow some correlation among these policies, it's in general correlated equilibrium. If you're familiar with game theory, you may have seen this, but this is nothing but a generalization of that to this dynamic game setting. Okay? Because we have state, we have a sequential decision-making problem. Still, I want to set up the stage by introducing these solution concepts. And one particular equilibrium, which is very ideal here, is team optimal, which is the best equilibrium if agents share the same work function. Because that's the optimal J you could achieve among all such equilibrium points. Okay. Yeah.
So you know the action, if you know AH, you know the action for all your neighbors, you're assuming?
Yes. No, we're not talking about learning yet. So it's just a dependence, right? Dependence-wise, yes. Dependence-wise, yes. So each Ri in general in this partial observable stochastic game or stochastic game in general is Ri depends on the joint action. Yeah. Other questions? Yeah.
Why not come out, the return is not discountable?
Sorry.
Why the discount factor is equal to 1 here?
Counterfactor.
In the discount factor.
Oh, sorry. Yeah, because this is finite Horizon setting. So we don't even take that to infinity, right? So we don't have to discount. I mean, in this case, you can incorporate gamma here to the power of h. Then you can also encode that into your R, like you can define R tilde, which is gamma to the power of h times this R. So that could be another definition of your reward. So in finite Horizon, usually people just sum it up. Yeah. Good. Great. So let's try to understand a little bit about, some ideas people use in empirical RL. So first idea people use is called privileged policy learning. In particular, actually, I talked with some students today. I think that's exactly what people are using in manipulation. Okay, as I will make it more clear. So in this case, we are actually starting this algorithm called expert distillation. In particular, that means that in training, I'm trying to learn a policy conditioned on this privileged information. So specifically, this is first of all, it's a very popular and intuitive approach that decouples policy learning into 2 steps. First, I want to learn an optimal, fully observable policy, like expert. Because at training time, I have access to that state, right? It's essentially MDP. So I want to learn an expert policy pi star, which is a mapping at each time step h from the state, because I can see the state, to a distribution, in general, distribution over the actions, with the help of this privileged information. Then I'm trying to distill this teacher policy into a student policy, which is partial observable. In particular, the function class I'm using here in this imitation learning problem, or like people also call empirical called the teacher-student learning, is partial observable. So pi, the student policy class here is conditioned on the tau h. Okay. And then there will also be some like behavioral policy to do the rollout. Okay. I'm trying to minimize the F divergence between this optimal expert policy and a student policy. Now here we'll consider even a simpler setting where let's say I'm directly minimizing the expectation, meaning I have like infinite number of data. Okay, I'm simplifying things by ignoring that statistical error even. Let's say you can compute this expectation, so that I can perfectly mimic this expert policy in this sense. I want to see if this works. Is the setup here? Great. There are many benefits of doing this. Why people use that? Because it's very simple. It's modular in the sense that it decouples how you learn this pi star in simulator and how you get the student policy. Okay. And also because in simulator you have access to state, it's easier for you to do exploration. We know in RL like exploitation trade-off is the key. But if you have access of state, at training time you can easily learn such a pi star. I just need to deploy that, distill that at testing phase. So the question we ask at the time is that does it always work? In fact, we show that it's not, even with relatively informative observations. In particular, what we can show is that you can easily construct a POM-DP, where observation is relatively informative. I will make it formal next, but still, and also with horizon just one. And the state also like space is very small even. There is a strict suboptimality gap compared to the best optimal partial policy you can achieve and the optimal distilled policy you get from that algorithm I just introduced. And this is a gap. Okay. And when I say relatively informative, I'm trying to introduce this context, this assumption. It's called gamma observability. Some of you may have seen this. So essentially, it means that if you give me two beliefs on the state, after you pass through that belief through this this emission function, I will have some separation. Meaning this observation channel is kind of informative in the sense that it separates my guess, my belief on this state slightly, if the beliefs are already different. Okay. Also, if you're familiar with control theory, it's also this notion is also related to the observability we study in control theory. We can show actually if it's this, if you have like a y, which is observation, y equal to cx plus some noise, if the same matrix is full rank, you can also show this kind of condition like in terms of observability like this. Okay, but in control, of course, we also talk about multi-step kind of observability, right? You have to check the full rankness of the gramming, but this is like a one-step version of that. You can think of that. So this is always just one step of emission function. I need that to be informative in this sense. Why is this important? Because recently people show that if you have this condition, you can solve POM-DP. You can have some efficient planning and learning algorithm to solve this POM-DP problem. Okay? It's a nice condition to have. What we show is that actually, even if the observation channel is kind of nice in this sense, but that method would fail in general. Okay. So the key idea here is also extremely simple. So key idea here is that you want to ensure the belief given the observation is kind of uniform across state. It's very uninformative, on which the expert will act differently. In particular, in this example, you can easily verify this problem is gamma observed. And this S1, S2 correspond to two different states. At different states, the expert will behave differently. Because on the left, the expert will pick the left action. On the right-hand side, the expert will pick the right action. But epsilon, you think of as a very small number. Okay? But we'll construct this prior and this likelihood such that if you compute the posterior distribution, given your O1, your guess or your belief on this state will be kind of uniform. It's one half. So there's no difference for me to guess, whether the current state is really S1 or S2. But because at different S1, S2, the expert will pick different action. Let's think of very symmetric action space there. Then the best imitation policy I should use is also uniform, given my O1. Okay, because eventually the student policy is partial. I cannot see the state. I can only see O1. Then it's kind of uniform. But this uniform is strictly worse. Okay, so this is the idea. Does that make sense? I hope I make the insight clear. If you have a question, please raise your hand. Yeah, sure, sorry.
Just going back to the previous one.
Sure.
I will just one slide after slide 20.
Okay.
I just have a question about why do we use one now? So if we step a little bit.
Sorry, why do you use what?
The one. So when you introduce.
Oh, you mean this condition?
Yeah. So
Yeah. I think that's a good question. I guess usually when people this condition was not introduced by us, it was introduced by, I would say, even earlier than in this paper. I think what they can show is just under this one norm condition, you can get a like quasi-polynomial time planning and learning algorithm. But whether there are some like a variant of that and that can also give you efficient planning and learning, I'm not exactly sure.
Because it's very natural to see if we're doing two norm that is.
Oh, but this is probability. So you're like total variation of one norm, right? That's what people measure, how they measure the difference instead of two norm. It's not a typical like vector, it's a probability. So in our theory, so for example, I want to measure the distance between like two probability transitions. Usually I would use like total variation of 1 norm. That's more typical than 2 norm.
Question.
Yeah.
Oh, so, is that right in probably
Sorry?
this V is a non-inclusion.
Yes.
And, that constant is a constant.
Yeah.
And I'm wondering, I think you can always rescale your reward function. You can always rescale your reward function.
Rescale, oh, okay.
So you multiply,
Yeah.
multiply contrast, but actually, I'd rather you change the speed usually. Whereas that constant is actually constant. So
No, first of all, in this setting, we have to fix the scale of each reward first. Yeah, let's say the reward in this case is 0, 1. So in total, the value is 0 to h. So that's fixed. We we wouldn't do that after we get the bound. So we fix that setup first, and then this is the arrow. So we fix the setup. Any other questions?
Remind us what epsilon was.
Epsilon is epsilon we had in this example. So basically, on the right hand side, you know, what's that minimum reward you get by choosing the next action. But essentially, inside I summarize here is that, so then we want to study when it works. So key observation here is that from this kind of example, the unseen state, the reason why it fails is because unseen state remain highly uncertain, even conditioned on this relatively informative history of observation so far. Okay? You don't have a good guess of the state yet. So this inspired us to make some assumptions. We'll make the following assumption. We call deterministic filter condition. This is a relative like a signal processing and control terminology I'm using here. Although you learned in that paper originally, people don't use this kind of name. So in particular, what I mean is that we say a POM DP satisfy this deterministic filter condition if satisfy the following. At step H, with deterministic prior, given the new observation and the new action, if the prior distribution is deterministic, the posterior distribution is also deterministic. In particular, that's equivalent to say that if you give me a history, finite history of O and A so far, I should be able to decode my state. It's called deterministic filter. If you think about like guessing the state as a filter, that's what we do. It's a deterministic process. You can also relax this to an absolute approximate version. Any questions for this condition? Basically saying that either your O or your A is informative for me to have a good guess of the state. Okay. So what does condition mean? That means the filtered state estimate, the latent state, is relatively deterministic. Interestingly, it covers several important known statistically tractable POM DP subclasses. So in RL theory, lately, people study several structural assumptions on this partial observable problems to make it at least statistically tractable, meaning it admits like polynomial sample complexity. So one well-studied setting there is block MDP, meaning that you can use one-step history, which is observation, to recover your state. Okay? Else it's not that different from a fully observable case, as you can imagine. That's a special case of this condition. Interestingly, there's another line of work in studying the sample efficiency of POM DPs. They study deterministic POM DPs, where the observation is general, but the transition is deterministic. It also turns out also to be a special case of the assumption we just made. Another class of problem people show is tractable statistically is called multi-step decodable, meaning you have a finite memory of history, okay, which people call it frame stacking in the deep reinforcement literature. If they assume these multi-step frames of images can decode the state, you can also have a sample efficient algorithm to solve this problem. These are all special classes of the condition I just introduced. In particular, our condition kind of unify this existing tractability assumptions in the sense that I always look at that through this figure. So the y-axis here corresponds to how deterministic the environment are. And the x-axis corresponds to how informative your observation. So basically, a tractable problem should be the problem you have a good balance of the two. You can either take it to the extreme, where as this paper assumes, where like the environment is totally deterministic. Think about a case where you apply like open loop controller, or like I'm closing my eyes while I'm driving, but if the system is very predictable, it should be easy. Or if I have a perfect sensor, like in MDP case, it's also tractable. We will try to kind of unify this kind of conditions by proposing this deterministic filter condition we just mentioned. It kind of naturally provide a trade-off between this observation informativeness and this transition determinism. Yeah.
So you're written under the K decodable form DP, the K should be a small constant.
Yes, because in those papers, their sample complexity would be exponential in K. Yeah. Any other questions? Cool. I'm have to speed up a little bit. Then under this condition, what can we do? So you can actually design a very simple modular approach where you can call any black box reinforcement algorithm to learn in MDP, learn an expert policy path star. And then you roll out this policy path star to collect trajectories and try to use this trajectory to learn this decoding function. Basically, because under this assumption, this decoding function, this decoder exists. You are able to decode your state using this history of information. On this condition, you can show that in the tabular setting where you don't do any function approximation, the expert distillation algorithm I introduced learns this absolute optimal policy with polynomial sample and time. Okay. You can also generalize that result to the function approximation setting with poly samples and polynomial cost to a classification oracle, which people believe is kind of tractable if you use function approximation. We can also generalize that to a multi-agent setting, but one tricky thing here is that when you do this rollout, you have to account for like the deviation of other agents, because when other agents are deviating, the trajectory will be different. If you think about a counterfactual kind of effect, that's why I have to be a little bit more careful when you are rolling out this trajectory to learn this decoding function. Up to that difference, you can still solve this problem in terms of finding like absolute Nash equilibrium in the zero-sum case, or like correlated equilibrium for general sum case with polynomial sample and time.
How crucial is that the behavior policy is the optimal policy?
Oh, it's very crucial in this case. But I guess if you make assumption, let's say if the behavior policy here has is covering this pi star, we should still be able to do it. You have like a mismatch coefficient like in terms of change of error argument, we should be still be able to do it. But you have to cover the optimal policy. Otherwise, it may be hard.
So in this be able to decoding setup, is it possible to construct another MDP, which like the state will be defining as, let's say, the past H states of the original?
Yeah, that's the POM. That's the original
practice.
POM DP. Yeah, that's the original POM DP.
No, I'm saying I define a new MDP.
Yeah.
And then the state will be S1, S2 up to S some L.
Oh, yeah.
For the original one.
Yes.
Then I make decision based on that small trajectory of states. Like,
You mean you can see the state, right? That's the MDP. That's
you can,
online.
no, based on the observation.
Oh,
Yeah.
you mean observation, action, observation,
Yes,
action?
you said like you can decode the state
Yeah.
based on past observations.
Right.
I just define a new MDP.
Yeah.
With the observation as states, but like the trajectory of observations as a state. And I
Oh,
do
I
standard
see,
RL
I see.
on that.
But if you good, but under our condition, which is relatively weaker than the decodable or once decodable case, is because we require the whole trajectory so far to decode that state. And if you don't do decoding, I think you are saying, right? A direct user history so far, it will grow over time.
If I truncate at certain point.
Then you need to make additional assumption to make it work. Because our assumption is weaker in the sense that you need the whole history so far to decode the state. It's not sufficient to just look at the finite window so far. But that's what actually exactly what previous some papers made assumption about. They assume like one shot can decode. But we need the whole history. That's why it will grow over time if you are not careful. Good question. Other questions? Okay, this is basically a summary of our results if you have privileged information compared to those results. For those results, if you want to make this problem of learning POM DP efficient in terms of sample efficiency, when we say oracle efficient, that means you can call this classification oracle if you have function approximation. Usually you need additional assumptions on this problem. Either you have like deterministic transition, or you need a very strong assumption on the observation channel. Okay? But by looking at the privileged information, you are able to improve the sample and computation complexity. And basically, we show that privileged information provides some benefits theoretically. That's the summary of this part. Let me quickly introduce this one. So the second idea, I think, also very popular. You use a lot. I will try to understand that. It's called privileged value learning. So in this case, people condition the value function on the privileged information, again, in the training only. Okay, previously was using that for policy learning, but now they are using this privileged information for value function learning. In particular, people call this asymmetric actor critique algorithm. In fact, this was the algorithm people use for learning learning dexterity for like robotic manipulation tasks like there. In particular, what it means is that it maintains a partially observable history-based actor, which is partially observable at testing time. But in the training time, they were trying to learn a fully observable state-based critique. If you're familiar with RL theory, reinforcement learning, you know that you have an actor critique kind of algorithm. Critique means that learning the Q function. They're learning that condition on the state they get to see at training phase. And then you can apply the standard actor critique algorithm, use this Q to update my time. And this is called asymmetric because they are conditioned on different information. So that is helpful intuitively because observation can be high dimensional in this case, that's the images. While states can be relatively low dimensional. And a fully observable critique may be easier to learn at the training phase. It's very useful in practice. We also asked, does it work? But in fact, the policy gradient for actor updates, right? Policy gradient for actor updates, estimated by this fully observable critique is biased. It's not very hard to imagine. And the correct, unbiased critique should also condition on the history. You should not just condition on the state. You should use your you should use your history to maintain a belief over the state. And then you take expectation over that as, like here, this is an unbiased estimator of the policy gradient. But if you only condition on state, this is not an unbiased estimator of the state. It's not only we identify this small problem here, but also like there's some other paper, they also identify this bias in this gradient estimator. In other words, this vanilla version, actually conditioning on the state is exactly the paper studied or used in this paper. Okay. We should be a little bit more careful when we are trying to develop actor critique methods based on this. So then our best version based on this policy gradient theorem is that we developed something called a belief weighted. This is probably the most technical slides in the whole talk. Basically, what we are trying to do here is that you're trying to update your policy in a certain way using your critique, your Q function. But because your Q function may be conditioned on your state, you have to figure out which expectation your state will be sampled from. If you are really sampled from the actual belief constructed from the system, then this is an unbiased estimator. And this, in fact, gives you a very nice policy gradient kind of update rule. And also, if you can do that for any h. So in the POM DP setting, you can consider this tau h, the history, as a state. Okay? It's a naive state, but it's a state. Very nice properties to preserve if you are doing an update on this tau. But there are two issues related to that. First of all, this tau h will grow exponentially in Python. Okay? A second issue here is that you really need to figure out what's the belief here. You need the system model, the system knowledge to really estimate this belief. So for the first issue, this kind of related to Xavier's question, which is if you make some assumption on the observation channel, in fact, you can do a finite memory truncation. You can control the size of the observation you are using in this policy update. Okay? It's not that hard. The second issue is kind of tricky here, because if you can, because you don't know the model, if you can have a very good approximation of your translation and observation channel, you should be able to get the following result, which is called belief contraction from the previous paper, meaning that you can estimate this belief very well. But in practice, in this POM DP example, you may not be able to estimate all the observation channels very well. Why? Because some of states are rarely visited even. You may not be able to even explore or even visit those states. You can, therefore, you cannot get enough samples at those states to try to make these observation channels well estimated. Now, how to do that? The very simple idea here is that we kind of maybe then probably those states they don't really matter anyways. So key idea is that we want to leverage this privilege information to get a good sense of whether these states are important or not by looking at the how many times I will be visiting this state when you have state information. If these states are relatively less frequently, those are not important anyways. I will do some redirection of, sorry.
Doesn't that require an assumption of the rewards? Like state may be listed relatively less often, but from a reward point of view, it might be like, suppose it's a safety example.
Yes, yes. So in this case, we are doing that without reward assumption because we are trying to evaluate whether this is important or not in terms of a reward-free set, in the sense any reward. Any reward. So in other words, the result we are using there is exactly from what we call the reward-free reinforcement learning. We are meaning that no matter which reward I give me, these states are not important anyways. I will only truncate those states. Yeah, very good question. We don't do reward, we don't use reward signal to help us do this. Instead, we try to find those states that are not important under any reward. And how to do that? We can assign those each reward with a constant each state with a constant reward, and so that I can explore all the possible states. If these states are never visited, then we should remove them. And then we will redirect those transitions into this highly carefully redirected to the states that's more frequently visited and construct another POM-DP. And then we're learning there. So that you can learn the belief very well. So that's actually one way to leverage this privilege information, because you don't have privilege information, we don't know the visitation of the states. So I think it's a kind of interesting way to leverage that in order to get the final result where you can learn the belief in a polynomial sample and computation complexity, as well as eventually you can get a poly sample and a quasi-polynomial time complexity for asymmetric active critique. And previously, you can also generalize that to the multi-agent setting for equilibrium learning. But previously, under this gamma observable assumption, you need quasi-polynomial time and the sample. But right now, basically, you can kill that sample complexity to just polynomial. But the time complexity, you cannot improve that because there's a fundamental result there showing that even if you know the model, planning this gamma observable model needs quasi-polynomial time. It's only more about sample efficiency. And yeah, if such guarantees are still possible under other conditions other than using like privilege information, that's still open. And also, I think without privilege information, let's say you don't have access to the state, the idea of partial history sharing from decentralized control theory actually has been very useful. We can actually show that under this framework, you can still try to benefit the computation sample by allowing the agents to share some information with each other. So that you can decrease the planning space you are doing on that common information. It's just a side note. If you're interested, we can talk more offline, but it's just a side note. Okay, last part, I really have to, sorry. Yeah, manipulations.
So what's on the left-hand side in the definition of real complexity? Like the error,
Suboptimality gap.
global
Like
optimality,
value, yes.
global optimality.
Yeah.
How does this function approximation error appear in that?
This is tabular.
Oh, this is tabular.
Yeah, tabular.
But in tabular natural policy gradient, the state distribution doesn't matter, right?
Why? What do you mean?
So like the tabular Bellman equation is
Yeah.
the
It
state.
is a POM-DP.
Oh, okay.
Yeah.
Okay. Okay, that's why in your MPG,
Yes.
You
Yeah,
have a-
on the history. Yes, exactly. Actually, in that way, we provide I would say not a very novel contribution, but there's some analysis of MPG in POM. But I would say that's very much similar in MD. Yeah, it's very expert problem. Okay, let me quickly jump to the last part of the talk. So that's our agents, but we're also very interested in like the LLM agents. In particular, there actually has been a lot of excitement recently, I would say even hypes of LLMs. So that caused a lot of sensations across academia, industry, and society. And some of the even like very theoretical researchers here, like Sebastian Bubeck and a bunch of people, they believe this is really the sparks of AGI. Yeah, they see a lot of excitement there. It's very interesting, very exciting. But also, I would say also a little bit hype there. Because of that, people have been developing this LLM as agent. Still, as I said, when I say agent, it means they interact with the environment, get feedback, and keep making decisions. The key is to use LLM as a brain for decision making and for reasoning. So one inspiring example of this research is from this very interesting paper called Generative Agents from Stanford. What they did is that they built a small town of 25 LLM agents in a sandbox environment with different roles. They just repeatedly interacting with each other as the time proceeds, and then they observe some social behaviors naturally emerge through such interactions. Okay, and information diffuses like, oh, someone wants to throw out a party at a particular time, and then they will just spread the words, and people just team up and show up. This kind of phenomenon, they observe that in this paper. They believe they are like believable simulacra of human behaviors. Yeah, people even use that for social studies. However, the question we ask is that, is LLM agent for decision making really a good idea, or even why that's a good idea? And how to quantify the emerging behaviors when multiple such agents interact with each other. Okay. So how to try to gather some understanding of this. So we start with a very canonical model because I like simple models so that we can have some understanding. Okay. So the model we study is a canonical model in sequential decision making called online learning. Many of you may have been familiar with that already. It has a deep connection to game theory and equilibrium computation. Okay. In particular, an agent interacts with the environment for T rounds. Every round, they will choose a policy, pi t, from a space, big pi, and keep doing that. After they commit to this policy, pi t, the environment will give them a loss. In this case, the loss minimization problem, which is a mapping from this policy to a boundary region. And in the simplest case, where let's say the loss is just a linear function, meaning it's a product between like a loss vector and the policy you choose. The policy right now lies in like a simplex, all the possible actions you are able to take. And this exactly corresponds to the expected value, expected loss you will be suffering at round t. You receive that? You can receive either like the full vector L or just a realized payoff, or sorry, realized cost you suffer for that particular action you take. That corresponds to the full information bandit feedback settings in this online learning literature. And then you repeat. Very simple model. So what's a good metric to solve this problem? So people develop metric like regret. Okay. It's probably simply the regret notion we have seen in this literature called external regret. Basically, that means the difference between the accumulated expected loss by implementing a certain algorithm that incurred, compare that with the best in hindsight fixed action you would have chosen if you know the whole sequence of loss. That corresponds to the second term, the comparator here. If you know all the L1 to LT afterwards, what's the best thing you should do? And the first term corresponds to the actual loss you suffer during this learning process. It's a reasonable agent should be able to be no regret, in the sense that it should be able to make this regret sublinear, in the sense that it's sublinear in time. Because it measures the robustness against like the arbitrary environments. And also if you have multiple such agents interacting with each other, this will lead to equilibrium. That's a folklore result in learning in games or equilibrium computation. It give you some meaningful metric if you have multiple such rational agents interacting with each other. People have been also using this no regret behavior as a model to predict human strategic behaviors with some empirical evidence. If you give me a sequence of things I need to make decisions for, this regret could be one potential good metric to measure the rationality of the decision maker's behavior. Any questions so far? Okay. Another quick thing to mention is that in order to be neurogat, there are several well-known algorithms, but the key idea is to first, I need to look at the history. I shouldn't be only looking at the current loss. I should be looking at the history in terms of making decisions. Okay, not be greedy. Secondly, I need to introduce some randomization. I should be unpredictable by the environment, meaning I should introduce either some randomization or some perturbation in order to be neurogat. So what we did is that we want to examine whether these LM agents have regret or not in this sense. If not, in some cases, why? And if so, in general, can we try to enhance it to be better neurogat agents in terms of decision making? So we did some experiments. We try to evaluate this kind of things on different large language models. At that time, we evaluated on GPT-4 models, also on Mixtra, Llama, which are open models. So interaction protocol is as following: H denotes human. The human explain the rule to the agent. So you are making decisions for like T rounds, let's say 50 rounds. At each round, you need to make a choice or choose a policy, and I will provide them the history of the play so far. You are making decisions based on look at, for example, you are investing in like a stock market. I give you the history of the decision you have made, as well as the reward you have received so far. And then tell me what's your next move, what's your next action you are going to take. And based on that, I will give back the feedback, which is like the loss vector to the agent, and I draw this window and ask them to keep making decisions. Okay, and then I will measure the regret. So this kind of, also you can do that in the repeated games that if you have multiple agents, then I will just assign this to like different agents. The payoff or the reward comes from a game. Online, there's a game there, and comes from the interaction among these agents. I will also count this, just compute this regret. This just, I will skip this one, just like the setup about how we generate those losses and how we try to generate those losses in an unbiased way. We don't want to leave the impression that, oh, we are trying to, for example, test them only on classical games like Prisoner's Dilemma, because they may have been trained on those data. We're trying to make it like randomly generated and trying to do more experiments to test. Also, it's a game setting. So you can see that actually in the online setting, can be no regret. In fact, sometimes in terms of regret, it can sometimes beat follow regret leader and follow perturb leader algorithms. Yeah. And also GPT series, they are better in that sense compared to open source models like Mixtra and Llama. We also did that in the game setting. Okay. All of them interacting, so they can achieve no regret in many cases you observed. And this is probably the fun part. Basically, we ask them to reason their behavior. Okay, so why did you choose this action at this round? So some of them seems to be behaving in a way that kind of introduce some idea we have introduced for this well-known neural algorithm, which is looking at the history, introducing some randomness. You give them the history of losses. They say, oh, probably I should be looking at the average of the numbers you gave me so far. And then I pick the best one, but still I don't want to be too predictable, or there are some inherent noise, inherent randomness in the decision making of these arms, so that by nature gives them some randomness in their decision. Okay. Of course, it's not universal. It's not very hard to construct failure cases such that LM is full. They cannot achieve no regret anymore. But funny thing is that it can easily succeed on a counter example that people use a lot to fail, like traditional algorithm, like follow the leader. In the follow leader basically means that you don't introduce randomization. Okay, I just take the average of the losses so far and then pick the best action. That's called follow the leader. This loss there is usually like in this alternating way. If the algorithm guess wrongly in the first round, then the regret will just accumulate. But LM can easily identify this pattern. They are not that naive. But if you add some noise onto that, like this, a noisy alternating we call it, so regret will blow up linearly. So it's not definitely not universal. I mean, quickly, I will probably introduce this very fast. So basically, we want to understand why, right? A highly hypothetical explanation of this is very much related to what people call it, this figure will explain everything, called in-context learning. So basically, if you explain all these like losses to them, you view them as a context you provide to the agent. So what they will do is that they will try to compute the average of that to have a good guess of what's really going on in the the latent space, in some latent space. But I think in context learning, let me first introduce that. Basically means that if you test LLM, right, you ask, let's say, I've input London, the UK, DC, the USA. If I input Beijing, they will output China. That's called in context learning. I don't need to tune the parameter of the large language models. I just provide them enough context. They will be able to, but why it works? A conceptual idea here is a Bayesian idea. Basically, by looking at these pairs of data, I will be able to guess the underlying concept Z here is nothing but guessing the country corresponding to that city. That's the underlying thing. I don't say it explicitly in the context, but LLM can guess that. There are a lot of results. I think recently they were trying to use this Bayesian idea, try to understand the in-context learning behavior. We'll try to connect this understanding with our online learning problem. Basically, if you give me a bunch of losses, if you make an additional assumption on like how they are generated, then the Bayesian learner will try to use this data to guess the underlying concept Z, which will be an empirical average. And then with some randomization, this becomes nothing but follow the perturbed leader algorithm. So we guess that's the reason why it can achieve the regret in some cases. I hope that makes sense. Okay. So basically, inherent randomness make it less predictable, and this in-context learning make it like looking at the history in a particular way, and exactly coincides with some more algorithm. Of course, that's just a conjecture we had. And finally, I think, of course, there are some failure cases where develop some new laws, which is since they were not designed for decision making, right? You shouldn't expect them to be always more bad. Why don't we enforce that, or why don't we incentivize them to be better more bad learners? So just ask them to minimize this regret. Okay? We have some like a very basic theory for the one-layer transformer case, very simple case. You can say something about this learning with this loss. But I would say probably the interesting part is the figure. So basically, these are the figures for the cases where the like GPT-4 would succeed. It's kind of expected. I mean, after training. Okay? But I would say interesting is this. So if you remember, these are the failure cases that these big models like GPT-4 fail. Okay? The noisy alternating case. But after you train over our like regret loss for this like very simple several layer of transformers, they are able to make the regret sublinear. But I have to be careful here because it's a little bit unfair comparison, because for this numerical model like transformers, we directly give them the input like the numeric values. But in these large language models, we give them like a long context, like a long prompt with the numeric values embedded in there. So it's not a very fair comparison. But what we show here is just like trying to show the idea that the regret minimization training could do something in terms of training a transformer. Let me summarize the last slides I have. Sorry for taking a little bit long. So takeaway of the talk. So basically, AI models are increasingly deployed as agents. It's a very hot topic people use a lot. So that they can interact with the world, with each other, with humans. However, current AI agents were not trained for it. Therefore, they require fundamentally different principles to build them in terms of what kind of guarantee can we have, what kind of fundamental limits should they be, and also in terms of new metric, new training loss, especially not just net token prediction, or like new data collection process and overall new training paradigm. And to address this problem, our attempt is that first of all, we start like RL agents. We get some insights from both deep RL, what empirical people are trying to solve this problem, and control theory to show the provable benefit of in terms of sampling and computation. Although some care is needed, for example, vanilla teacher-student learning and the vanilla asymmetric actor critique may have some problem. We have to be careful, especially for the applied researchers here. And for LLM agents, want to get a more principled understanding in controlled and canonical settings with new training laws that can promote their decision-making capability. The last comment I'll make here is that, so I'm neither suggesting this is the right way to solve online learning or games. We have so many algorithms online, like for the record speed or for the we definitely shouldn't be viewing this as a way to solve or as a new way to solve online learning problems. Nor we should view it as a right way of using LLM. Okay, it should be able to solve more complicated problems. But I guess this test is just a very simple and toy example to just maybe make myself or some people in the audience a little bit more comfortable about using them. And if they cannot have some, understanding on the performance on this task, it's not very comfortable for me to use them on more complicated tasks. I mean, maybe less comfortable depending on how you interpret the results. Okay. And I would say this is just a very initial and fun exploration, and definitely we posted more questions than we were able to solve. I welcome everyone to try to look more into this very exciting area and try to get a better understanding of it. And that concludes my talk. Thank you so much.
Thank you for the great talk. We have time for questions. So I had a simple question in the follow the regularized data that you hypothesize. How does the LLM learn how much perturbation to introduce?
Yeah, that's a good question. We don't know. We don't know. Actually, in the small theory we had there, we had to make some assumption. So basically, like it's under that Gaussian data assumption, that's follow the perturb leader. But if any of the assumption breaks, the coefficient, which is step size, in those update rule would not be the optimal one. We know from the theory, so it shouldn't be Noroga in that case. But we don't know in general. Yes, we don't know. I still have to mention that even if the step size is not optimal, but they may still be able to perform Noroga behavior. So that's possible, especially in like the losses you provide. It's not universal. So yeah.
Other questions?
Fine tuning, yes, exactly. But in our paper, it's not even fine tuning because we were not able to get that trained on large models. We're only training that for like 1 layer, 2 layer transformers. So it's like in that sense, it's training from scratch. Actually, it's just a simple model. But what we are really actually trying out right now, what we are trying to do is try to deploy that actually on big models, which is definitely happening in the fine tuning phase. Because pre-training is like it's not the same thing. For fine tuning, for pre-training, I think the universal loss there is next token prediction. The collect a lot of data, predict next token, but this is definitely for fine tuning, so that they can be better decision makers. That's the idea. Yeah.
So for the first part of the talk, so are there fundamental challenges to generalize the result to infinitesimalism or
Yeah, good question.
or stochastic shortest path?
I guess in infinite horizon, things become stationary. So like some of things you are learning, for example, decoding function and all that would be like a stationary function. I'm not exactly sure. We haven't thought about that yet.
And then in one of your assumptions, you mentioned like you disregard states that are not visited often for any reward model.
Any reward.
So this is essentially a structural assumption on the underlying Markov chain. So essentially under any policy,
Yes.
the station
Any
distribution
Yes.
is somehow, let's say, very small for some
Yes.
state.
Exactly.
But you're working with finite horizon setting, right? So it's like the station distribution of the MDP does not matter.
It's not stationary. Even like you have finite steps, but there is still probability of visiting each state at each time. It's non-stationary for sure, but that's definitely a probability. So we are talking about that probability, not the stationary one. Yeah.
Okay, that's good.
Yeah, and the only way why you can do it because you have privileged information, and that's a way to leverage that.
Thanks.
I understand the first part of the talk is that you have the privileged information from the simulation, and then you look at the clear works and so on. Are you assuming that the state space in the simulation and the model is
The same.
any comments on? when it's different than it.
Good question, good question. That's like a bigger like symmetrical gap, I guess. I guess that's very, I think our framework cannot address that for now. But I guess in control, we know like model over reduction, right? Or we may be able to model that difference. We were not able to do it here. Or we go to the continuous space linear system setting, maybe it's easier to address that issue. For the finite state action case, I feel like maybe all you need some state abstraction or aggregation in order to model such a misspecification. But we haven't done that, and I haven't seen that. Actually, I haven't seen many results of this model specification in Tom DP anyways. Yeah, probably that's the right, the right thing to work. Definitely, that's a very good question. In practice, definitely there's a gap.
So maybe it's a combination of robust RL plus.
Yes, like you can plug in this robust RL to model that also.
Yeah,
Oh, yeah.
from the first part of your talk, so I was trying to get a better understanding of this privilege information. So for example, suppose that you have a problem of functional approximation in the multi-agent setting.
Okay.
Then what would be the privilege information for the agents?
First of all, the privilege information here has nothing to do with function approximation or not. Even tabular case, you could have privilege information.
Yeah.
In the multi-agent setting, the privilege information is first of all the state, underlying state, and also other agents' observation. So for example, in self-driving car, like if you deploy the policy, you can only see like your surroundings, right? The pedestrians and other cars near you.
Yeah.
But in the training phase, you may be able to see other agents' observation. So that's the setup. This CTDE centralized training, decentralized execution is all about. Yeah. It's independent, perpendicular to this function approximation thing. Yeah. Oh yeah.
Just to follow up with that question, I was also thinking about understanding on
Right.
the base problem. And so if I understand it right, the observation model is mapping the previous information to the observed, like partially observed information. And my question is, where does that observation model come from? Is it like
You mean in practice or in this model?
practice?
In practice, just like a sensor, right? So basically the sensor is to measure the state, but think about case where the sensor may not be perfect. So it will always give you something that's with noise, or maybe it's just a partial view. Think about like the vision-based manipulation, for example. You only get one single view of this object or like of this thing, but that's definitely not necessarily the right state there. It's just a partial view of this problem. So that's where the partial observability comes from. Either the noises or like some unmodeled dynamics or like this partial view of the problem. Truncation. I can only see part of the object.
Got it.
Yeah, that's an example.
There are no more questions. Let's start Kaiqing again.
Thank you.
I would like to chat to him. I'm sure he would be happy to. He's here for 10, 15 minutes.
Yeah.